So I'm going to talk about the Nernst equation. Um, I have already made like notes on it, but like in this video, I just want to kind of go through how the equation works um, in a more like dynamic way, so you can probably understand my notes a little bit better. Well, I can understand it a bit better. So the Nernst equation is basically a way for you to figure out the electrical potential when the the galvanic cell is not under the standard condition. So you see that this equation basically tells you that the the E value um it depends on the concentration of both the oxidized species and the reduced species. You can see from the equation here. It all relies on the concentration of those two species. And while the standard electrode potential it has a certain standard condition. The standard conditions are 101 kPa or 1 atm for pressure, 298 Kelvin for temperature, and you must have 1.00 mole per dm cubed if you have any like electrolytes in the galvanic cell. By electrolyte, I mean like the this is how like your galvanic cell looks like. There's like a cross bridge. You have like electrolytes here. I mean electrodes here, connected to like a voltmeter. And here, down here, you have like solutions. These solutions might be 1.00 mole per dm cubed if you're recording the standard electrode potential. But if you're actually running like a galvanic cell, this does not happen. So I think most of the cases, if you're just trying to do the reaction, you won't get like a perfect 1 mole per dm cubed, 298 kelvins. You won't have the standard conditions. So that's why we have this equation for us to calculate the electrode potential when we're using a non-standard condition. Okay, so let me just quickly break down this equation. We have the electrode potential equals to the standard electrode potential, which is basically you have your whatever half cell compared to a standard hydrogen potential so you get a standard electrode potential, which is for reduction, the reduction process. And you also have plus 0.059 divided by the number of electrons transferred in the reaction, and you log the concentration of oxidized species over the reduced species. So this equation infers this relationship. So there are two situations you can have. One is that if you use a inner electrode, basically what's taken in part of this reaction is only the aqueous solutions that you have in the both of the two beakers. However, if you have like a metal or metal ion electrode, you know that the metal itself will be either oxidizing or reducing. So basically it will be participating in the reaction. So it's a slightly different scenario. So for the first one, it's quite straightforward. So on top you have the oxidized species concentration. Under here you have the reduced species concentration. And since both of them are aqueous, you can just straight away use their concentration values, no problem, and they will be provided. But if you have a metal or metal ion electrode, since the electrode will be a solid, and here you see the solid, the solid concentration, it definitely does not change because, well, solid is a thing that, imagine like you have like a, how should I say this? Um, let's just imagine you have like a big chunk of sugar or something, and even if I break it down into like really, really small powder or pieces, it's still the same concentration. Meaning, like in one, like if I compare one powder of sugar to like one big chunk of sugar, the amount of sweetness is probably the same. I'm not sure if this is a good explanation, but basically the concentration does not change. So since the concentration of anything that's solid does not change at all, or gas, the concentration of gas and solid will be constant. This is really important here. And since they're constant, you can basically ignore it. So yeah, so hence the equation will look like the same, just that you don't have to divide it by like a solid or gas. You can just straight away log 10 the oxidized species. So that's the two situations you can have. So this is my first example. This one will be the situation 1, where I have an inner electrode and where both of my reactants are, both of my half cells have like aqueous solutions in it. So look at this. Calculate the value of the electrode potential at the 298 kelvins. So far I can see that the temperature is still standard of a Fe3 plus, Fe3 plus and Fe2 plus electrode that has a concentration of Fe3 plus ions of 0.50 mole per dn cubed. So this is a part that changed, if you can recognize, because our standard condition requires our solutions to be exactly 1 mole per dm cubed. But this is 0.5, so it's not the standard. So this part different from standard. And okay, but if you see right here, the Fe2 plus ions have a concentration of 1.0 mole per dm cubed, which is the standard. This is the standard. So I think, well, before I go on to like explain the rest of my answers, I'm gonna explain why this part is quite significant. So the reason is that well, actually I think ignore what I've just said. I think both of these values actually they can be like non-standard. Like this one, it could be like some other random values like 0.75. That's no problem. I can still use the equation as usual. However, if you just want to measure like the change in E value because of the change in one of the concentration changes, you better keep the other ion with the standard concentration. So let me rephrase that like a little bit. So I think the reason that now we're keeping one of the aqueous ions with a standard concentration, the 1.0 mole per dm cubed, but we're changing one of the ions concentration to a non-standard. The reason that we only change one but keep the other standard is that we want to measure how does changing the concentration of Fe3 plus ions actually affect the electropotential value. Because this way we can straight away see the effect in the change in electropotential. But if we change like both of these values, then we won't know which concentration change has actually changed this value here. So that's why we will choose to keep like one of these concentrations standard. Okay, let's proceed to the question. So from the half cell, like how it's written here, I can write down like the equation. This is the half equation that we're gonna use, and I'll just identify like the reduced direction and the oxidized direction. So I have done that. And bear in mind, so after writing down the half equation based on the half cell we're provided, I need to check my standard electrode potential, because that tells me whether my reaction, my half equation, will be feasible or not. So from the plus sign, I know that this half equation, this reaction, is going to mostly go to the forward. It favors the forward reaction because the sign is positive. This tells me that the reduction reaction is much more favored than the oxidation. So therefore, we're gonna have like, at the end we'll have like a lot of Fe2 plus compared to Fe3 plus, which actually makes sense here because my Fe3 plus value is smaller than that of the Fe2 plus value. So that basically tells me after I run this galvanic cell for some time, after I run it for some time, I will have a increase probably in the Fe2 plus concentration, and a decrease in Fe3 plus, because this equation, this reaction, it favors the forward reaction more. Okay, so just now in the equation, we talked about the oxidized species and the reduced species. And if I were to define that, you can just look at how I wrote these under here. So in the reduction, if I just write this half equation into, split it into like one reduction process and one oxidation process, this one is basically like the reverse of that one. I can see that for the reduction process, I will say my end product of the reduction, I'll call it reduced species. Whereas for the end product of my oxidation process, I'll call this my oxidized species. So hence I know the Fe3 plus is my oxidized species, I'll put it on top. The Fe2 plus is the reduced species, I'll put it on the bottom. So I can then substitute my values in. This is my standard electropotential, we'll sub it in. And from this equation, I would say that the number of electrons that were involved is only 1. So therefore, this is where the 1 came from. And then I just substitute the concentration of Fe3 plus in here, Fe2 plus in here, just following the equation, and then I'll get this value, plus 0.75. Now, note that this value is actually a bit lower than the standard electrode potential. So the reason is actually that if you look at this if you look at this equation right here, and we just look at the question, we'll see that for Fe3 plus ions, our concentration have decreased from the standard. What I mean is that, I'll write this down here. I'll use a brighter pen. For standard, so what I mean by standard is how we have previously achieved the I naught. We achieved the standard value being E naught equals to plus 0.77, I believe. Yeah. This value is achieved by using like a Fe3 plus aqueous solution of 1.00 mole per dm cubed. And a Fe2 plus aqueous of 1.00 mole per dm cubed. But now in my non-standard, something has changed. Well, my Fe2 plus still has a concentration of 1.00 mole per dm cubed. But my Fe3 plus, this is what has changed. It changed to 0.5 mole per dm cubed. So you see there's a decrease in the concentration of the oxidized species. And if you just think about this whole equation then using math, if this decreases, that will lead to a decrease in my overall E value. So hence this is why my overall E value, 0.75, is lower than my standard E value, 0.77.